So, in our course we will be next looking into another topic which is finite state machine. So, to some extent we have already seen some finite state machine as the name suggests. So, this finite state machine, it has got a number of states and the system it transits through those states as time passes, okay. And the number of states that you have in the system is finite, it has got a fixed a finite number of states, and that is known a priori. So, you have to design a system that has got a known number of states, and the transitions between the states are also known, and accordingly we have to design a circuit. For example, if we are talking about a vending machine, okay. So, in a vending machine operation initially, so there are some slots into which the coins are to be put. After the coins have been put, the buyer can select the item that he or she wants to buy, and then if the money is sufficient, then the good has to be disposed. So, that goes in a sequence of events, okay. So, whenever we have got this type of application, so they come under the broad heading of finite state machine. So, we will be looking into some this finite state machine designs in this part of the lecture. So, a finite state machine is an electronic machine which has some external input, externally visible outputs, and some internal states. So, output and next state, it depends on inputs and current state. So, output and next state, so both will depend on the input value and currently whatever state the system is in. So, based on that it will depend. So, it is the abstract model of a finite state machine is like this. So, it is a 4 tuple, a machine M is a 4 tuple consisting of 4 states, 4 quantities S, I, O and delta, where S is a finite set of states, okay. Then the system at any point of time, or the machine at any point of time can be in any of those states. For example, if I say that my state set S is consisting of the states S1, S2, S3 and S4, what it means is that at any point of time machine will be in one of these 4 states S1, S2, S3 and S4. So, it cannot be in any other state, okay. So, they are all excluded. For example, if your machine is a counter, and if you are thinking about a mod 16 counter, then this set S is the set of states 0 to 15. On the other hand, if it is a decade counter, then the set of states S is a are the values, so are the states 0 to 9. So, that way depending upon the system, the machine that we are having, this set of state will be determining the states in which the system or the machine can be at any point of time. Then I is the finite set of inputs. So, it interacts, the machine interacts with the environment, accordingly it gets some input from the outside, and that is that there is a finite set of input. Then O is a finite set of outputs. With respect to that vending machine example, so when the coins are being put into the system, or the user is giving a choice regarding the good that he or she wants to buy, so they are coming as input to the system. And when it is disposing the good by means of activating some switch, so that is basically the output for that machine. So, we have got this I and O, and this delta, so this is the state transition function. So, that defines how the state is transiting from one state or one state to the next state. So, next state depends on the present input and the present state. So, this state transition, so this is determined by the present state and the next state. Of course, there is another function which is not written here explicitly, which is the output function. So, output function, so this is basically it is often represented by lambda. So, this lambda actually tells, so lambda over any state say S I and some input combination say I j. So, this will be telling us what is the output value, say okay, for all the outputs. So, it will tell me what is the value of the output. So, we will come to this slowly as we proceed. Okay. So, from the automata theory, so you can visualize this structure, this machine like this, as if we have got some register, and this register is clocked, and this register holds the current state of the system. So, this current state comes as input to a combinational logic, and the inputs that are there, so that also come as a combinational logic, and this combinational logic, so it determines what should be the output and also what is the next state. So, this next state values will be stored again in this register as the current state. At the next clock pulse, this next state values will be stored into this register as current state, and they will be available as current state. So, this way the system will be passing through different states, and depending upon the input combination, so it will produce some output, also it will make transitions. Now, inputs are coming from the external world, outputs are also given to the external world, the states are internal, and the combinational logic is also there, which is determining these two functions. So, let us take an example. Suppose we have got a system that has got a switch which may be either up or down, and an output which may be either on or off. So, you can think about the electrical switch and a lamp. So, if the switch is in switch may be in either up or down position, similarly the lamp may be in on or off situation, and the system has got 4 states A, B, C and D. So, when the system is in A state, so when the system is in A state, if you press the switch in the upward direction, then the light should be off. So, it is as long as the switch is pressed in is kept in the up position, the light is kept off, and the system remains in state A. If you take this switch down, okay, so then the light is turned on, and the system makes a transition to state B, and as long as the switch is in down position, so it will be remaining in state B and the light will be turned on. Then if the switch is now put into the up position, then it comes to state C and puts the light off, and as long as as long as it is in state C, as long as you are putting this thing switch in the up position, so it will remain in the off state, and if you put the switch in the down position from C, then the light remains off, and similarly at the D state also, if you put it in the up position, the light remains off. If you put it in the down position, then also the light remains off. So, once you are in state D, okay, you see that in all the so light is always kept off. So, whether you put the switch up or down, then the switch will light will remain off. Only when you are in going to state A, then if you put the switch down, then it will be turned on, and then after that if you are state B, then as long as it is down, it will be on. So, this is a hypothetical behavior of a system, okay, that has got is some input switch and some output which can be turned on or off. And then this input, so this is the an example of finite state machine. So, it has got 4 states A, B, C, D. Now, in these notations, so there are some symbols. Okay. So, some we write it like this. So, this state, so it is normally a state is given like this, and if it is put within a it is 2 concentric circles, like here there is another circle which is surrounding this state name. So, that is the start state. Okay. So, any start state, any arbitrary state transition diagram if you draw, then to indicate the start state. So, if suppose I have got some arbitrary state transition diagram like this, to mean that this is the start state. So, I have to make it like this. So, if there are 2 circles, then that is a start state, or it may be the other symbol is like other symbol sometimes used is like this. Okay. So, that is the start state without any symbol coming, without any labeling like that. And whenever a transition is occurring, so we label it in terms like input / output, like so everywhere all these transitions that we have. So, you see that the labeling is input, we first write down the input condition that will trigger that transition, and then after the slash we write down what is the value of the output signals. So, that is the so in this case we have got a single output signal. So, that's why we have got only one output. So, if there are multiple output signals, so they can be put here. Similarly, if there is a complex input combination condition, so that will be forming a Boolean expression, and that can be written as the left part of this before this slash. So, this way we can represent a finite state machine by means of some diagram. Okay. So, mathematically we can write it in terms of those delta and lambda functions in graphical notation. We can draw the diagram, and then that also represents the finite state machine. So, this is a slightly complex example where I have got this I0, I1, I2. There are 3 input, more number of inputs, okay, I0, I1, I2. So, we can have similarly as I was telling. So, there may be more number of outputs also. So, if this is the input combination, so this should be the output combination. So, that is the meaning of this labeling. Similarly, for the states, so instead of showing it by some name, so you can also show them by means of the state the register content. Like here I am writing here 00, that means the state register contains 00, and when the state register contains 00, if the input is 0, output will be 0 and it will remain in the state 00. Similarly, if the input is 1, then it will make a transition to the such that the state register content becomes 01 and the output is 1. So, it will remain there. So, it goes on like this. So, here this as if this states A, B, C and D, they have been given a 2-bit code. State A is coded as 00, B as 01, C as 10 and D as 11. So, this we will come back to this coding again later. So, as if these states have been given some name or some code. Now, the type of machine that we were looking so far, so they are known as Mealy machine. So, in case of Mealy machine, what happens is that outputs and next state function, they depend both of them depend on they depend on the current state as well as the input value. So, this output function and the next state function, they depend on the current state value and the input value. So, they depend on both the values. So, this is the standard Mealy machine, the standard finite state machine that we have seen so far. So, they form the Mealy machine category. So, another combination, another type of machine that we can think about. So, it is Murray machine. So, where the current this outputs depend only on the current state. So, this is input is not determining the current state, input is determining only the next state part. So, the current state component and input, so they are determining the next state part, whereas this output is determined only by the current state. So, input is not determining the output, sorry, the input is not determining the output, output is dependent only on the current state. For this type of configuration, so it is said to be Murray machine. So, apparently it seems that the Mealy machine and Murray machine, they are two different types of machines. So, maybe one of them is more powerful than the other, but that is not the case, both the machines are equally powerful. So, you whatever computation you want to represent using Mealy machine, so you can do it using Murray machine and vice versa. But circuit wise, of course, since this Murray machine, the output is dependent only on the current state, it may so happen that it has got more number of states. Because in case of Mealy machine, what will happen is from a particular state for different input combinations, so you can have different outputs, but for Murray machine that is not possible. So, for all those different output combinations, so maybe we have to have separate states. So, that makes Murray machine to have more number of states. So, here an example of this Murray machine based FSM. So, here you see that individual states, so from the age level, so we have dropped the output, because output is not dependent on the input, it is dependent on the current state only. So, in state A, the output is always off, at state B it is always on, similarly at state C and state D also they are always off. So, this is an example of Murray machine. Whereas, for Mealy machine, so this is the standard example that we have previously seen. So, output is dependent on the current state as well as the input combination. For example, if the current state is A, input is up, then only the output is off, whereas from the current state A, if the input is down, then the output is on. So, that way output is dependent on the current state as well as input, which is not the case for the Murray machine. So, we can try to take some examples to see and understand how these finite state machines can be designed. So, a very simple finite state machine that we can think about, suppose we are adding two infinite input bit streams. So, this is some adder. So, what it does is that it there are two infinite bit streams and accordingly it does this addition. So, it adds first these two bits 0 and 1 comes here, as a result. So, these two bits are added, the result is 1. So, it is outputting this 1. Then this 1 and 1 comes. So, sum is 0. So, it is outputting this 0 here, and there is one carry. So, when the next two bits are coming, so this one carry is also taken into consideration as well, as a result. So, this bit becomes 1, and then this generates one carry. So, this carry is taken to the next bit addition, and that is done by 0, that is the result is 0. But the point is that it at any point of time it just adds 2 bits. So, it remembers what was the result of this previous addition, whether it had generated a carry or not, and based on that it is producing the next result. So, if we try to do this do realize this finite state machine, so it is like this. So, if this is the initial state, then we can say that if the next input combination is say 0 0, then the output is 0 and it goes to a state where the carry was equal to 0. Whereas, if the input was say 0 1 or 1 0, in both the cases output is equal to 1 and it comes to a new state. Or we can do it like this, we can make it slightly better. Actually, we need to distinguish between the two cases. In one case the carry is generated and in the other case the carry is not generated. So, so from this I can say if it is 0 0, the output should be 0 and it goes to this state. If it is say 0 1 or 1 0, if it is 0 1 or 1 0, in those cases the output should be equal to 1 and it goes to that state. Okay. So, in this state, so you see that what we have got is the output, there was no carry generated. Now, if from this state, if the output, if the input pattern was 1 1, the 2 bits was 1 1, then the result should be 0 and it comes to a state where it remembers that a carry was generated, there was a carry. Now, from this state, if the next 2 bits are 0 0, then it has to output a 1 because the carry was generated and we do not have any carry. So, we can say that if the next bit is 0 1 or 1 0, in that case it has to output a 0, okay, and it goes back to this state. On the other hand, if this state is from this state, if it is if the next 2 bits are again 1 1, then it has to output a, if the 2 bits are 1, then it has to output a 1 and it should go to a state where it has to generate a carry again. So, in this way you can complete this diagram and it will turn out to be a finite state machine by looking into all the combinations. So, essentially from a particular state you have to see the next 2 inputs and accordingly go to the corresponding bit. So, this design is slightly complex. So, let us look into another simpler example for our understanding. So, this is the exercise. So, I am leaving it for you. So, you just do it. So, let us look into the D flip flop, how does it behave, or D latch or D flip flop. So, in terms of finite state machine. So, you see that this is a so if I say that at present the Q output is 0, then if the D is equal to 0, then it will remain in this state and output will remain as 0. If D equal to 1, it will come to a state where the output is 1, and as long as D is equal to 1, it will remain in this state. When D becomes equal to 0, it comes to this. So, this is the finite state machine that represents the behavior of D latch or D flip flop, and this is a Murray machine because output is determined by the state. Okay. So, this in state 0 output is 0 and in state 1 output is 1, and if you do a minimization you find that Q nu equal to D. Okay. So, Another example, a 2-bit counter. So, the counter starts at 0 and at every clock pulse, so it increments by 1. So, first it outputs 0 0, then at the next clock pulse it comes to 0 1, next clock pulse it comes to 1 0, then 1 1, then 0 0. Again this is a Murray machine because the output is determined by the input, okay, by the current state. So, this is 0 0 or 0 1, etc. So, if you want to design the corresponding circuit, then what we have to do is you have to find the expression for H nu and L nu, and accordingly you can design the circuit. So, this H nu and L nu, so if you derive, then the H nu, L nu is given by this expression, which is L old dash, L old bar, and H nu is given by this expression. So, essentially what you have to do is that you have to take this H and L, 2 flip flops, and then we can do this minimization, that is L nu is given by this L old dash. So, this Q bar line is connected here and it is done like this, and this one your H nu is given by this expression H old bar and L old. So, this is AND OR gate based realization, this is NAND gate based realization, otherwise it is same. So, this way our finite state machine is this one, and from there we could come to a circuit which realizes the finite state machine. Now, if that counter that we are talking about, it has got a reset input, like here this counter has got a reset input. So, here this if reset equal to 0, then it behaves in the normal fashion, but whenever this reset input is equal to 1, whatever be the state in which the counter is, so it will come to this state 0 0. Okay. So, it will be outputting 0 0. So, that is captured here. So, you see whenever R is equal to 1, whatever be the values of this H old and L old, H nu and L nu will be 0. Similarly, when R equal to 0, it behaves as a normal counter and it goes like this. So, L nu is given by this expression and H nu is given by this expression. So, we can make the corresponding circuit. So, this is the corresponding circuit which realizes the 2-bit counter with reset. Next example that we will look into is a counter with 7 segment display. So, we have got a 7 segment display with A, B, C, D, E, F, G, and each segment in the display can be lit independently to allow all 10 decimal digits to be displayed. Okay. So, this is 0, 1, 2, 3 like that, and there will be a 2-bit counter, we will need to display the digits 0 to 3. So, we will output a 1 for each segment to be lit for a given step. So, for 0, so this is a for 0, so this will be output, it will turn on these segments, for 1 it will turn on these 2 segments, for 2 it will turn on these 2 segments. So, this will go in a fashion like 0 1 2 3 0 1 2 3 like that. So, from 0 0 from 0 0, so it has to go to 0 1, from 0 1 it has to go. So, this is the state transition from 0 to 1, 1 to 2, 2 to 3, 3 to 0, and if this reset is 1, then it does not matter whatever be the state. So, it will come to the state 0 0. Now, we have to see what is the pattern for this 7 segment display A, B, C, D, E, F, G. Now, for displaying 1, we know that for displaying this these G segments, for displaying this 0, so the only this G segment should be off and all other segments should be 1. So, that is done here. So, at the current state for 0 0, so it is turning on A, B, C, D, E, F and G is equal to 0. Next, at the state 0 1, so this we have to display 1, accordingly segments B and C they should be turned on and the rest of the segments they should be turned off or put 0. So, this way we can write down the truth table for this A, B, C, D, E, F, G and then do a minimization. So, A becomes A and D they are similar and this is the expression for A and D, B equal to R dash, C equal to this one and E equal to this. So, this way you can have this all the expressions for these 7 segments, okay, and they can be fed to the individual logic. So, we can have this 7 segment display and this A, B, C, D, E, F, G, those lines are connected to the 7 segments and these two counters. So, once it is reset, so this counter values will become 0 0, from that point onwards. So, it can go on getting the individual values. it can go on getting the individual values. Another example that we will look into is the 101 lock. So, this 101 lock is like this. So, we have got this whenever this pattern 101 is observed. So, the lock is said to be open. So, it starts in a state where we have seen only a 0. Now, if b equal to 0, so this is the start state. So, if I as long as we see b equal to 0, so it is we have seen a 0, b equal to 1. So, it comes to a state which is which we call 1 scene and the output is 0. Then if b equal to 0, it comes to the state 10 scene and the output is 0, and b equal to 1, it is 101 scene and this output becomes equal to 1. Again it has to look for this 101. So, again it is 1 scene. So, it is comes to output is 0, it comes to 1 scene, then 10. So, like that this finite state machine is made. So, accordingly you can draw the corresponding truth table and get these signals realized. So, this 101 combinational lock can be realized by these functions, and then it can be converted into some circuit for getting the thing.